Obviously, I'm not Professor Chenoy, as you have realized by now, hopefully. My name is Mike Zink. Professor Chenoy is traveling, and so he asked me if I could give a kind of, a guest lecture today in class and talk a little bit about our work in multimedia streaming, kind of the problems and the research work we've done in this area. What I would like to do is also, keep this as interactive as possible. I don't know you very well, and I don't exactly know what you have been, what concrete topics you've talked about in class. But go back and ask any kind of questions you have during class. I enjoy that. I usually then understand how much you're following or not following. So if anything is unclear, whatever, or if you have anything in addition you would want to have clarified, please feel free to ask any questions about this. Right. Also, I walk around a little bit, quite a bit. So if I'm and if you can't read the slide, let me know. Just give me a sign to get out of the way. But I tend to make a hike during a lecture usually. So my name is Mike Zink. I'm actually a professor in the ECE department, but I'm also an adjunct professor here in the computer science department. I have been, before I became a professor over there, been a research professor here. So, I know this department very well. I know some of you. And I know some of the professors here very well and have been working together with them for a long time. And actually, some of this work I'm presenting here is joint work with Professor Caruso. So we're looking into, hey, good morning. I know this guy too. Good morning. So we want to look a little bit into the issues of multimedia streaming. And before I get started, I want to tell you a little bit how important this is. Right, so when you latest Sandvine statistics show that at prime time, so 8 to 10 o'clock at night, 50% of the downstream traffic into the access networks, right, is Netflix traffic, right? So streaming video is like a big, chore, so to speak, for the internet, because there's a lot of bits and packets we have to get to the viewers. And, it's also interesting because what I find interesting is I find this really interesting because I think we're seeing a change in what's happening, right? In the, 10 years back, everyone had, their cable, their satellite, and now we're going more and more to this online, right? My kids sometimes, sometimes I have them, they're very small, I have them watch something on PBS, and they want to, when my son says, I got to go to the restroom, can you stop it? And I say, no. And he's so used from watching things online that he doesn't realize when we watch regular broadcast that you can't stop it, right? And so these kids grow up with a completely new paradigm. And we see this more and more. If you've seen, Netflix is making their own shows, right? They have like House of Cards and there's the Mitt Romney documentary and so on, which is probably unthinkable 5 years ago. So this is changing the whole landscape, so to speak. And one thing that's also interesting, I had to think about, is actually the way this is going. What's actually happening with all the satellite providers, DirecTV and Dish Network, right? I don't know if they're still, but the more and more I watch stuff online, they're not really an internet provider, right? What's going to happen with them in the future? I honestly think they're going to be in a little bit of trouble pretty shortly because what's the service they really have to offer long term, right? Right now they're just offering everything that's on broadcast. And my feeling is that people less and less will watch broadcast. Live sports events will still be a driver for a long time. You have 50 million people watching Super Bowl and stuff like that. But it'll be more and more on demand and much more personalized in the future. So keeping that in mind, I wanna, if you don't mind me saying it this way, I want to throw some numbers at you, right? So look at the challenges we have, right? So when we look at the multimedia server and also the proxies, and I will go into proxy caches in a moment and define them a little bit clearer. When you do continuous media stream, just 4,000 movies, right? 90 minutes, we take 90 minutes movies. If we look at just this regular DVD, that's 27 terabytes. If we look at, in 50 Mbps format, a little bit higher quality format, that's 40.5 terabytes. If we look at Blu-ray, which is kind of becoming more and more a standard, we're looking at 97.2 terabytes just to store that information. Right? There's a lot of data. Right? The good old days of CDs, right? 2,000 CDs of 74 minutes, 1.4 Mbps, only 1.4 terabytes, right? Little side note: you guys know why CDs had to be able to play 74 minutes of music? when the standard was defined, they wanted to have, I forgot which one, but a certain, I think it was a Beethoven symphony that had to fit on a CD, and that was like 74 minutes. So sometimes kind of funny where these numbers come from. I know this because my advisor back in Germany was with Philips at the time when they did all this CD standardization, and it was in the midst of that. So kind of interesting side note, right? So look at these numbers, right? The really, high volume numbers. It's almost like big data. Everyone's talking big data these days. It's almost big data. But the challenge we have with this is also, what is the challenge with it? We have high volume, but when you think of video streaming, what's one of the challenges you can think of? If you have a file, like say this is all, this would be a file distribution system. What kind of, researchers distributing data from the Hubble telescope or some hyperspectral images, which is also high volume, right? What's the difference with video?
You can't have too much latency.
Excellent, right? It's real time. It's real time or quasi real time, right? If you get a packet, we have frame rates, right? It's like on TV. A frame has to be shown in certain intervals. If that data for a new frame comes too late, what happens? It's buffering, right? Or you have at least some decrease in the quality of the image, right? So that's another challenge. That's very different to what we do with files, right? Now the problem with that is, as you probably know, the internet as a network is not giving you any guarantees. It's still best effort, right? It's kind of amazing how well this works when you watch a video these days, right? And so we're going to look at some of the stuff and some of the work we've done to kind of see how we can deal with the challenges and improve them. So when you look at the servers, right, there's this high I/O challenge. We talked about the constraints and we talked about this high data volume. So you have many concurrent clients, right? I thought if you look at the numbers, like even if you look at Google press statistics, how many users are on YouTube, for example, right? There's millions of users watching videos. Netflix, there's probably millions also. It's real time, right? It's continuous play out. We have like for DVD 4 Mbps. Up to 10 Mbps, for HDTV 15 Mbps up to 36 Mbps, right? And the capabilities of the disks we have in these systems, like a 400 Mbps throughput on a regular Seagate, and an SSD 1.2 GPS gigabits per second. So they might be a little bit higher by now. It's a little bit older numbers, but still, this is one of the constraints. And then the network, right? 1, 10, sometimes you have 40 gig interfaces. I don't know if you can get 100 gig interfaces for switches right now. I don't think you can get it for servers at the moment. Or if you have to pay a fortune, so to speak, to this. And then the buses, right? Our regular PCI bus limited at 8 gigabits per second, and then the PCI Express at 64 gigabits per second. Right? So if you look at the single piece of hardware, you see all these bottlenecks, all these constraints of being able to deliver many parallel video streams, right? And so what comes in addition is that there's computation going on. Encryption, sometimes there's encryption because of copyright and all these kind of things. Sometimes transcoding has to be done, and sometimes adaptation, because as I mentioned before, the internet is a best effort internet, and we don't always have the maximum bandwidth available. And so transcoding means that we on the fly change from one format to another to adapt to the available bitrate. There's other formats like a scalable video, where you have a video that's encoded in layers, and you have to choose from what set of layers or how many layers you can transmit based on the bandwidth that's available between the server and the client. Right? But a lot of constraints are because of this high load, and you see where the bottlenecks are. So this is an uphill battle, right? This is kind of what we have to do. So what I want to take a quick look at multimedia servers. And actually, when I talk about multimedia servers, I mean this not only as like what we call the origin server, where the content origin server, but also a proxy cache or a cache. As we have web caches, we also have video caches, right? Which pretty much have the same functionality than a server, not always hold the complete content, the complete video library. And then I'll talk a little bit about the work we did of analyzing the YouTube streaming system, and then how we can improve performance of such systems by looking at the caching, prefetching, and the recommendation systems that come with all these online video services at the moment. So the hierarchy, as you can think of, right, what you have here is like you have a bunch of master or origin servers that hold the video library, the content video library. and then you have regional servers, and then local cache servers, right? And so depending on what content is on the servers, the clients are served from one of these three layers. I talk of this in layers. And so the good thing is, if you have if you can manage to store a video that's very popular here, then you can serve a lot of these requests from this server, and all the load that would come from this server and go in the backbone and go up to these servers is taken off, right? So this is a good thing that makes our system more scalable. Now, I want you to think about two things. One thing. There's actually a huge difference between services that provide professional content and services that provide user-generated content. A service that provides professional content is Netflix, right? You see videos produced in Hollywood, they're very professionally produced. If you look at YouTube, it's mostly quite the opposite, right? It's me holding a camera and filming my kids or something like this, right? So, so if you think of that, when you think of popularity, right? When you can manage that a little bit different when you have professionally generated content, because you know when something new is being published, so to speak. So Netflix, for example, I think they're kind of bound to the limits of the studios, so they cannot make a movie available online before it also is available on DVD or Blu-ray, right? So they know kind of the date, and so they can actually, they can pre-distribute this information, right? With YouTube, it's pretty much impossible, right? And the problem is also with YouTube, if you look at the popularity distribution, we have a long tail distribution, right? There's a lot of videos, there's tons of videos that I only watch 1.5 times, right? On average, so to speak. And so how do you deal with that problem? We're going to talk about this a little bit more. So here, if you go across all layers, you have, somehow you have all the content available, right? You hit one of these servers at some point in time that has the content, right? But what you want ideally is actually find that content as low as possible in the hierarchy, because it makes the system scalable and keeps traffic off the backbone. As you might know, these content providers, they pay a lot of money to have thick pipes to their server, right? And the thicker they have to design the pipe, the more money they pay. So if they can keep it a little thinner, they save quite a bit of money. There's kind of, I think I talked. I think I mentioned everything that's on that slide. Any questions so far? Good. So one thing I want to talk about, we talked about, before we go in the bigger system picture, I want to talk about the server itself, or just give you a quick idea of what's going on with the server, right? And so what we have is, if you look in your operating system, you have your user space and your kernel space, right? You have the file system and the communication system in your kernel space, and you have your application on top of it, right? So what's the application these days for video streaming? What do you use to serve videos, or what's used to serve videos most of the time? The browser, right? So sorry, in this case, the video server. Let's go back, the web server, and you use a browser to retrieve your video, right? So the application is a web server. And so what happens is actually you have to go from the user space to the kernel to retrieve the data from a disk, right? And then, send it through the communication system out. Pretty inefficient, right? You have all these context changes, right? Between the two spaces. There's actually, if you're interested, there's quite a bit of research how you can do this actually in the kernel, right? To make video servers efficient. Paul Halvorsen from the University of Oslo had an Infocom paper in almost 10 years back, 2005, 2006, to see how you can actually not go through the application space and just do this in the kernel to make this more efficient. So you actually see the way how we do streaming these days, right? If we use a regular web server, it's just not really efficient, right? Because we have to pull the data all that way up to the user space and then kick it down in the kernel again to send it out. Okay, so there's this important resources, right? The memory, the buses, the CPU, the storage system, and the communication system. We talked about some of the capacities of these right now, right? And you can see what all the bottlenecks are and how they deal with it. And as I mentioned, there's a lot of optimization you can do. There's a lot of interesting work. There's tons of papers you can read if you look at like all the publications in the last 10 years and like from the ACM Multimedia Conference, ACM Multimedia Systems. One of the things, for example, is called batching. So what you could do is, right, what's not shown here or so far, we always assume that if I request a video and you request a video, that's always two individual streams. Now, if you think you had multicast in the internet, right, where you can send from one sender to multiple receivers, you could do something. If I want to watch the same video as you, we could, and I start first, right, we could delay that a little bit, right? And delay it if you have high requests, for example, for a new video, right? Then you can delay that a little bit and then wait with my playout until you request it. And so then, via multicast, these two requests can handle by one streams. This is a little bit of load reduction for the server, right? So there's tons of work in this area, and so I want to talk a little bit about the work in my area in a second. So you mentioned the timeliness, right? So delay is an issue. So if we have the data offset here, right, our bytes for the video, and if we have time over here, this is kind of, if you had a variable rate video, this is how the data has to arrive to be played out on time. Right? For simple, to make the discussion a little bit easier, we just assume this is a constant bitrate video, right? And so this is how you have to receive the data to play it out without any problems, without any buffering, without any impairments, and so on. Now, to do that, right, you have to start retrieving the data much earlier, right? So what you have to do is the data must arrive before the consumption time. So this is usually why we all have a little bit of a buffer for each video, right? So your video basically never starts right away, right? It always takes, a little bit of time. Sometimes it takes a little bit more time, sometimes it takes a little bit less time. It depends on network connectivity and a couple other issues. Excuse me. So the data must arrive before that. And then, sure, there's a network in between, right? So you must actually, to have it arrive on that time, you must send it much earlier, right? And then also you have to retrieve it much earlier, right? You have to get it from the disk, because you get it from the disk and then have to ship it out. Lots of time. These times are not exactly at scale, just to give you an idea. But that's kind of all that time that leads up to your buffer time, right? And depending on where you stream it from, right? As you can imagine, with between the send and receive, if you stream it from a cache that's close by, that's a little smaller. If you cache it from the origin server that's on the west coast or something, this probably is quite a bit larger, right? So that's for example why this has also an impact on how long you buffer, right? How long your buffering time is. It's usually dynamically calculated, right? So that's kind of what you have to keep in mind. If that line crosses, if the dark green line crosses the light green line, you're in trouble, so to speak, right? That's when you underrun your buffer runs empty, and you cannot display a new frame, and then you have, the little clock show up or whatever. Right? Let me pause here. You're smiling. It happens to you once in a while, right? So let me pause here and see if you have any questions about this. I think this is kind of a fundamental thing. I want to make sure everyone is understood. Okay, am I too fast? Am I speed okay? Just let me know. Good. So what we did a while ago is actually we had the luxury that actually Jim and Prashant and my colleague Tim Wolf over in ECE, they wrote a grant and they got a nice measurement box on campus. And that measurement box sat right at the gateway router to the internet. And we can observe data. And we use that just to analyze what the YouTube traffic is that's coming in and out of campus. I just want to see that and observe that, and then take that for some analysis. So we did some measurements, right, just to observe. Right? Because one thing we can always learn from is observing what's really happening, how are users, using a service. There's this, if you look at all the prominent measurement conferences, you see these kind of things happening a lot, not only for like video services, but for other networking services, for routing and wireless services, qualities of that. And so, right? So what we could do is actually measure that. So what I will do in the next 20 minutes or so, I'll talk about the motivation for that work, the measurements we performed, and then how we use that measurement actually to look at how how two distribution infrastructures, a peer-to-peer based one and a proxy cached one, would improve the overall system, right? And then talk a little bit about what we learned. So again, I mentioned that before. This is a lot more. This was like around 2010 or so. YouTube serves up to 100 million videos a day online. I think it's 400 right now. I forgot the number correctly. Recently, if you go to the Google public relations site or the YouTube public relations site, they have the latest statistics on it. So it's a lot. It's a lot of demand to that system. And at the time, we weren't clear. We now know that they're using a caching hierarchy, but at the time, I don't know what they had in place. They had a content distribution network in place, but not any caching. Right? So we looked at the things, and as I mentioned before, access to YouTube is different from a regular professionally created video, professional content created video on demand service, as I mentioned earlier. And we want to see kind of how the access from a campus network is. And the nice thing is actually the campus network gives you kind of a nice scenario of an access network, right? This could be a regional access network. We have, I don't know how many nodes, but we have, sometimes several 10,000 of clients here. It makes sense to have, a cache, right, on campus because it's a good kind of customer base. And actually what we learned, we didn't know this at the time, and I think it wasn't in place, but over the years we learned that actually we have Akamai caches. You guys know what Akamai is? Who does not know what Akamai is? Akamai is a content distribution service. So when you for example go to the CNN webpage, right? You cannot lead every request to Atlanta, right? So what they do is they have an agreement with CNN that they replicate the information from CNN on different servers across the world, and there's a DNS mechanism behind it. So when you connect to it, you get redirected to the closest cache. And there's one sitting here on campus, and there's a Google cache on campus, right? So actually our implications at that point in time were kind of not too far off because the customer base, if I can say it this way, is big enough to use those caches. And then we want to see what kind of correlation we even have between global and local popularity. Can we use global popularity to make some predictions on what to cache or not locally? The methodology, we used the YouTube traffic on the campus gateway. We also obtained the global popularity. You get that for each video from the Google statistics, from the YouTube statistics. We analyzed the traffic, and then we used trace-driven simulations. So we used the information we got from our measurements to drive simulations to see how caching and prefetching perform, how proxy-based and peer-to-peer caching performs. So here's a scenario. It's changed slightly, but the main mechanisms are still the same. When you want to request a video, when you get a HTTP GET message, then the original server sends you a redirect to the content distribution network server, and you get that. You get redirected. You send that GET message, and then you get at the time it was Flash video. You get this, and this is just how the HTTP messages looked like. And our monitoring box at the time was sitting right here, so we could capture that traffic. Right? It's all anonymized, because we don't want, the university NYT makes sure that everyone's privacy is protected in this case. So we can get this information and get some data from it. So we used the HTML information, and then what we used also, we constructed a flow to obtain the duration of the streaming session, the average data rate, and the amount of transferred payload data. And so we took a couple traces. You see here, there's one that is a whole month. No, this is only 1 day. Sorry, this is only 12 hours. This is 72 hours and then 108 hours. And here you see the different unique clients we could see doing these measurements, and then the per video stats, how many videos were requested, and how many of these videos were requested only once, and how many of these videos were requested multiple times. So you see that actually the potential for caching is only with these ones, right? So that's relatively low because this is one of the characteristics we have with YouTube. That it's user generated content. There's a few very, very popular videos, and then there's this long tail of videos that can watch once or twice. Okay, so that's the data we obtained from that with our measurement. And so here you see the different traces and the popularity of the clips, and you see actually exactly what I described before with the long tail. Right, this is log. As you can see, the long tail, and then only a few that are have a really high popularity. So all of them down here are you cannot caching them doesn't make sense. Okay, but nevertheless, we want to see. Wait, there's one more slide I want to show you. This is actually we just looked at. Shows a little bit differently. What do we show here? The requests per video over the overall requests, and we show the ones, here you can actually see some of the videos were requested over 80 times. So the same video was requested over 80 times. Actually, there was one requested 140 times, but you can see here the majority of them that only requested once down here, right? So only everything beyond that bar here is actually what would make sense to cache, right? Just for a little bit of a further analysis. What we also did is then, for each video we saw these traces, right? We looked at our local popularity based on the distributions we could determine here, and then compared that with the global popularity. So you go online and you look at the number of views, right, and compare that with all the videos we had in the trace. And we actually saw that there was pretty much no correlation. If you look at the correlation, this is very low correlation, like this here, between the global and the local popularity. So the downside of that is when you initially we thought if there's a strong correlation, what you could have done is if there's a video requested, right, and it's not in your cache, and you look at the global popularity and it's highly popular, you would decide to cache it, right, because that would be an indicator that someone else would request the same video. Unfortunately, not the case, not working, right. And we said, when we realized that neither, if you see, we have different lengths. We did take different lengths of measurements. That doesn't have an impact, or the number of clients. If you go back to that table here, right, we had different numbers of clients. Here, the number of clients is much lower. As you see, this is in June. All the students are gone, so we have less clients here. Didn't have an impact on that. But we found, I don't know if this is still online. If you go to that link, we found a video that was made by students here at UMass, and that had a very high popularity in one of the traces. So, local popularity, videos of local interest have higher popularity. And you might find that maybe now again, so, the university actually produces now, professionally made videos and puts them on YouTube to advertise UMass, and that might be something interesting to put on the cache, right? Just kind of even just as a replica, because people might watch that. It would be interesting to see. We can actually now identify if a video is served from the local cache or not. We should actually try that out at some point to see where this is coming. Okay, so we looked also. We did a video specific analysis. Oh, I apologize. This is somewhat cut off here a little bit, but this is just for the third trace here. We also did a client-specific analysis. And so what we're showing here is the number of requests, or the number of clients with requests, 100 with request 10, and so on. And so you see here that that there's a lot of clients that only request one video, and there's a few clients. There's one client here where you always have this one client very active, or two clients in this case actually very active. No, that's the one. What am I doing? Sorry, here's the one. That has like 800 views. So someone must have been done with all the exams and could read these, right? So now this is not true, right? Because there's one issue we're dealing with, right? So I think there's NAT and DHCP, at least for the DHCP definitely for the dorms, and so we cannot exactly say that an different IP address, but the same IP address is also always the same client. There's nothing we can do about that. It's just adding a little bit of error to this. But so you could probably cut off the outliers. But I would believe, knowing my kids, that there's some that watch 100 YouTube videos a day. So that's definitely possible. So so we had the video clips with multiple requests, total number of requests, and the maximum number of requests per client. And we see here these requests. Okay, so a little bit of a client analysis because we also wanted to see if it makes sense to cache just at the client or also cache as a using peer-to-peer as a caching. And so what we did then is actually we looked into what kind of distribution infrastructures would make sense, and we looked at a cache-based one and a peer-to-peer based one. Before we did that, for our simulations, we did other analysis. We looked at results from the stream flow analysis. So from the first trace, we looked at the duration, the length of viewing, right? So there was actually a 99-minute video. No, there was a 99. Sorry, this is all seconds. There's a 99-second video. There was some very short video, and then you see a 4,422 was the longest we had in our traces, right? So just to see, kind of have a distribution of how long the content is, how many packets, what the payload size is, and what the rate is. On average, the maximum rate and the minimum rate of each of the single flows we observed with the monitoring. Just to get a little bit more analysis about all the flows here. We see the average stays pretty much the same. It's a little lower here. So we had this information because we just, when we did the caching, we wanted to make some assumptions. We couldn't, we didn't want to, we want to make some assumptions for how much storage is actually also used when a video is cached, right? So we used this data we got here from the measurement. So the first idea was, let's look at a peer-to-peer approach. So the idea is, client A requests video A at time t, and then at time t plus x, client B requests the same video, but instead of going all the way back to the orange server, it's redirected to client A. Right? Now, as you know, with peer-to-peer systems, that has, it's very highly scalable, right? But the disadvantage is the churn, right? This guy can come and go at any point in time, and so, how does this work? So, what we did is actually here we just, I think this is let me think for a moment. Yes, this is where we varied the local cache size of the client, right? This is so from 10 to 10 megabit to gigabit to 10 gigabit, right? And looked at the cache hit rate in our simulations, and you see that you get a slight improvement. Interestingly enough, is that for trace 1, it's pretty flat, right? You're not getting too much improvement, although it's much higher for trace 2 and trace 3. And I think here we just assumed that the clients are on all the time. We actually also did a window-based availability approach. So what we did is we did simulations where we said when that client requested that video, we gave it, and we said, and we made an assumption that we used different time units. We said this client was online so many minutes before and so many minutes afterwards, and looked at where the window sizes and what kind of impact that has on the cache rate. And obviously, if you increase the window size, the cache rate goes up. We did this with a fixed cache size, where probably some of the break, I think maybe with 100 megabit or so, to look that up in the field. And the client availability obviously influences this bit rate, right? So there's the cool thing about this is you don't need any extra infrastructure. It's highly scalable, right? The downside with this is it's not reliable. If the client shuts down, it's gone, right? Go ahead.
Yeah, the question was
Yeah.
if the client B has started watching a video of say X seconds or X minutes after client A has, so one can predict that by the time the video finishes and client A logs out, there would be the window would be there would be a delay of X of X seconds. So so one could sort of predict that if this is the time client A is going to go off, at that moment client B could preempt a connection to the original server and get it done.
Absolutely.
So that way some of it
Very good point. Yeah. So there would be definitely one alternative to do that. Right. Absolutely. So the other one is the infrastructure one, where you really assume you add a proxy cache to the gateway and serve the whole access network. And what we did here in the simulations, we just assumed the regular FIFO replacement. So whenever the cache is full, what came in first is deleted first. And so if you look here, it's actually kind of interesting because the traces perform relatively similar in terms of hit rate, right? You don't see that as much as a difference as in this case. And then, oops. And then you see how the hit rate improves, and that kind of forgot. 100 meg, a gig, 10 gig. So at 100 gigabyte, right? You kind of see this whole thing leveling off. So that shows. Oh, actually, I have the number down here. Just read. so with a relatively low-cost solution, right? You needed cache at this point of time. You would have needed a cache with 100 gig, right? You cannot buy 100 disk anymore. It's kind of one terabyte is the standard, I guess, by now. So you could have used a builder or install a cache that achieves the maximum achievable or supports the maximum achievable hit rate based on the request you have from the user. So that's kind of a relatively easy solution. And so I swear that Google didn't have a cache on our campus at this point in time, but I know since 2012 they actually have a cache, so they must have seen some of that effectivity or effectiveness themselves in the data set, right? It really helps reducing the backbone traffic. The university also has an interest in that, right? Because the university pays also for the thickness of the pipe that's going to Internet 2 and the commercial provider, right? So if less traffic goes out for YouTube, that's also good for IT because their bit is a little bit small, right? What I want to mention is also related work, right? So we're not the only ones who have been looking in this. There was Chidol who have been looking at this, but they also only looked at data from the YouTube server. They didn't have a local trace. They just looked at popularity analysis on a very high level. And then there was Gil et al., who had similar to motivation to ours, but they had only a predefined set of servers that could be monitored. The CDN service, so they could not get as complete trace as ours. And I think they didn't run as much. I don't know if they run all the simulations we had, but it was kind of interesting because the trends between both of our data, or both of our results were clearly in agreement. Okay. Yeah, go ahead.
You said that there's a Google cache someplace on the network here. Is
Yeah.
that like university owns it? Like Google owns it?
No, I believe Google owns it.
What was that?
I believe Google owns it.
Google actually owns
Yeah.
and they installed it here for their benefit to offload their load?
I think it's a two-way benefit, right? So I know for a fact that Akamai has a cache on campus and Google has a cache on campus. And we've seen that through some of our measurements, right? And so the benefit is, as I mentioned before, so the university is connected, I think it's connected to 3 providers actually. One is Internet 2, it's the research network of the United States, right? The second one is Level 3, which is a commercial internet backbone provider. And then I think QWest is still the third one. And I think the third one is really kind of a backup link they're using if something goes on.
It goes out to Worcester, I think.
Yeah. But so for Internet 2, you pay, I think they pay kind of a fixed fee as a membership for being an Internet 2 member, right? But for Level 3, university pays volume based, right? So now if they have, I don't know, like 2 terabyte a month, or just let's take any number, they pay X amount of money, right? If they have 300 terabytes, they pay more, right? Now if you have caches on campus, as you can see, you can reduce some of the traffic that goes out into the backbone, right? And so you save some money on that side. So that's an interest for the university, right? We want to save money, obviously, right? The other side, if you take the Akamai or the Google side, is they have less load on their servers, right? If you can get this from the cache, so that's why it's a two-way interest, right? Does that make sense? Okay, how are we doing time-wise? We have until 10 past, right? 10 past 10? Or 15, quarter past 10? Oh, 20. Cool. I have lots of things to talk about. We had, in this case, not done any simulated studies on different distribution architectures than the one I showed. There's no, well, I think I mentioned it all, there's no strong correlation between local and global popularity. Neither the length of the measurement nor the number of clients had an effect on the correlation. We showed that video clips of local interest have a high local popularity. showed how alternative distribution infrastructures could, help with reducing traffic. And actually, also one thing I forgot to mention is if you have something closer by, right? So your delay is much shorter, and the other thing is so the shorter latency, and then also most likely less potential for bottlenecks. So you get a high, most likely a higher, experience of watching the video with less pauses and better quality. So the other thing we looked then into a couple of years later is actually what about if you have a local cache or even for your client, if you prefetch already a little bit of the content. So the benefit with prefetching is that you get a little bit of a bigger buffer. Right? When I show you the graph with when the data arrives and when you have to send it. So like just let's assume for now, mysteriously, the system knows what you're going to watch next, right? So ideally, we could start, prefetching that information if you had a list that's large enough. And then you could start streaming that, right? And so if you had like a good chunk of that data already locally on your machine, on your hard disk, for example, then you could live with periods where the bandwidth kind of is lower than the bandwidth you need to stream that in real time, right? Because you would deplete your buffer a little bit, but you would shrink your buffer, but you would not completely deplete it. Right? And so that was another approach we looked into, and the idea was, here again to look at, because video streaming is becoming so popular, to look at the recommendation system. Right? Does the recommendation system help us with it, right? We're not any magicians or whatever. We cannot predict what users are going to watch next, but all these systems kind of try to help the user with telling them what to watch next, right? So we could potentially see it. And so what we did is actually, I talked about the problem, right? So if you prefetch, you hopefully avoid this kind of buffering issues. So what we did first is actually we looked at what's the current situation actually, right? So at this time we did a measurement from kind of different locations, from the university here, from a company, from home, apartment, from dorms, other apartments. I think that was me traveling at some point in time, even from a hotel, right? Kind of what kind of experiments do we have when we watch videos, right? And so here are the results. There was a really high likelihood that you would experience pauses, right? So this was for watching YouTube videos, so I should have mentioned that. And so here you have the different environments, and the blues in these bars show you actually the ones where the users experience pauses. As you can see, my hotel connection was horrible, but that must have been more an access network problem, so we're a bit of an outlier. But you can see out of the 41 playbacks, out of the 170 playbacks, 41 contain pauses. Right? And the interesting thing is, as the next slide, is if you were to experience a pause, it was really very likely that you would experience more pauses. So 31 out of 170 playouts contained more than 10 pauses. And that's super annoying when you watch a YouTube video, right? Even if you watch a 90-minute video, 10 pauses, it gets kind of, at least for me, it gets annoying. But if you watch a short clip, that's not great. Actually, a little bit later on, actually last year, Professor Ramesh Sitaram had an IMC paper that talks about, that actually they have observed that if, based on trace data they obtain, even 2 seconds of a pause can make the user go away and do something else. And that's really bad for a service like YouTube. Why is that bad? No revenue from commercials. Right? If you go and do something else, you're not watching their commercials, no money. Right? They're not making any money. So if you think of that, you want to avoid this, right? So how can we improve that? And so the idea was to kind of look at a prefetching agent. And so we have 2 scenarios here, where you have a prefetching agent that again could sit on a proxy on the gateway to the access network, or you could have one that sits actually on each on the individual clients. Right? So two approaches. And so this prefetching agent selects videos to be prefetched and retrieves their prefixes. How long of a prefix we'll talk about it. And stores the prefetched videos. And there's two approaches, you know, the prefetching on the client base, where you directly do it locally just for your client, or with the proxy, where you do it kind of for everyone in the subnet can and then the idea is, can we somewhat predict the videos that are most likely to be watched, right? If we could do this perfectly, that would be really, really effective. So what we do is actually the PA determines videos to prefetch from incoming requests. So what you do is actually, so we have this recommended, so there's two ways, right? On YouTube you can search, or you have what's called the related list, right? And so what you can use in this case is actually when someone requests a video, you look, if it's done by search, you get a list. If it's just the next video, you get the related list. And now you can actually start prefetching the prefixes for the videos that are listed in these two lists, right? And so and then you can actually see the related list. I know that for sure has 20. But you can say, I only do the top 5, do the top 6, top 10, right? So you can look at different approaches here. The nice advantage about this is it's very simple, right? You have the data at hand. The cache, the only thing the cache has to do is it has to intercept that HTML data that's coming down and do a little bit of parsing of it. We've actually, for some other work, written a parser for our own work, and it's really easy, and it's not putting much strain on the system. You don't require any additional data. You have to not go to the YouTube server or whatever information. Now the question is, how effective is that? It's a simple approach, but is it also effective? Again, we like analyzing that based on real-world traces. Here we had a couple newer traces, 1 day, 3 day, and a 7 day trace from 2009 and 2010. Here you have the number of requests. As you can see also here, this, you know, never do any measurements during break times. This was winter break, right? So you see how the requests actually go down. Although this is 3 times longer than this one. The number of unique clients and the number of unique views. What we did then in addition is we looked at all the videos that had been requested in these traces and retrieved the search result list and the related video list via the YouTube API. And so you have that information too. And so we could then run analysis. And then what we also figured out, what we also looked into is how often do the users actually use the related list or the search result. And at the point in time, YouTube had added a little tag to each URL when you requested from the related list or when it was from the search. And so that helped us greatly with identifying that. Unfortunately, the length of the packet we specified for the captures was too short for the first trace, so we didn't have the whole HTTP message in there, right? So we couldn't see that part of the HTML of the URL because we truncated our traces too short. So, you know, one of the lessons you learn when you do measurements, right? You know, never get it right the first time. So with trace 2 and trace 3, we had the full URL, and so we could see how percentage of requests came from the related video list, the search results, and then from YouTube pages, and then from external links. Right? And you see there's actually related video list and search results are around 30%. Right? That is actually, we have later data where this actually increases to 40, and there's a paper from some other folks, they have seen it with up to 60%. Right? So it's very popular. People use that quite a bit. Okay, so that's good news for us, right? They use it. So if you prefetch based on that, hopefully that works out, right? So evaluation metric is, you know, we again run trace-based simulations based on the real user requests, keep track of the videos in the prefetching agent storage, and then the evaluation metric is the hit ratio, where we look at the hit requests compared to all. So the hit request is when you request a video and the prefix is already on the cache or on your local machine, compared to all the requests in the trace, right? And so, excuse me, here we have a graph as I told you, right, these lists show up to 20 videos. I know search even shows more, but the related list at least. And so we looked at how does this perform if we, prefetch the top 5, the top 10, the top 15, up to the top 25, right? And then looked at the hit ratio. So, and we looked at 5 different approaches. This is just with a regular cache. It's just a regular caching approach, no prefetching anything. So you get a 0.4, you get 40% hit ratio. If you do search related where you just do it for the client, that's the worst performing, right? If you do search related with the proxy, that performs a little bit better. But the related list performs much better. Now, what kind of, if you go back to this, this is one of these moments where you look at the data and have to unfortunately start scratching your head, because the usage of these two is not too much different, right? So, now, too bad, back to the drawing board. Actually, new challenge, something more research to do. So, good or bad news, whichever way you want to see it, right? So what we did is actually, well, before I get to this, one more thing I want to show you, sorry, is actually that, if you combine caching and prefetching, right? So if you do the regular caching and add the prefetching of the related list or search results videos on top, you can reach up to 80% hit ratio, right? It's pretty cool. We saw much lower, we were at almost 30% for the older traces I showed you in the first part here. And so that's very nice improvement and really helps with reducing load, right? So I told you about this problem with, why does the related list prefetching work so well? And so we looked into where are the hits actually coming from. So if we have n, right, and how many we prefetch. So you have here what are the requests for this? External links, search results, related video list, or just from YouTube pages. And you see that actually only up to half of the hit requests come from the related video list. Right? Here, these violet ones. The search results is also a good chunk of that list, especially in the PF proxy caching. Sorry, I should have mentioned this is the client results and this is the proxy results. And you see that here, right? They're pretty much almost half of. Related video is a little bit higher. The recommendation system is like, is a good kind of indicator for topic interest. And what we realized is that some of the related videos, were watched by other users automatically, and others overlap with what was searched for. So sometimes, the problem is you start a search, right, and then you click on your first video, and then you go into the related. You watch more from the related list, right? So that's kind of how we got this overlap and why we got this very good hit rate. So the recommendation system is kind of interesting, right? You can actually use the recommendation system to improve the performance of the cache or the prefetching, right? And so that's just what I said. That the related video list, video requests generated from other, they overlap with requests generated from other resources, and that was especially in the proxy case. That was the case. So we looked at this. We also wanted to know how much storage do we need for that approach, right? And so if you have a cache only, right, this is flat because you just do caching. No, I'm not doing prefetching. You need what's that? 200 gig or something like this, right? And what we did is we measured this in slots that slot holds one prefix of a video. So 2.5 megabits would be assumed to hold 30% prefix size of an average video of 8.4 megabits. And we only require 85 terabytes for reach 81% hit ratio with M21, right? So this is here where you see the prefetch only, and then the combination of cache and prefetch and the storage requirements. Right. Go ahead.
Doesn't this increase your bandwidth usage though? Because if you're fetching...
Give me a moment. Very good question. Very good question. So, so the impact on the storage space, we looked at, again, here on the x-axis you see the storage space in terms of slots, and you know how the hit rate increases for all these different approaches. We looked at how many meters prefetch with increasing storage rates, right? And it kind of linearly increases here for all these approaches. But even with a 125 gig disk at the proxy, you can get a 60%. Okay. So the question is, should we prefetch the whole video, right? And so what we did is, what we see here is what kind of average start buffer size, based on the trace data we had when we did this initial measurement. We looked at how much buffer would we have needed to have a flawless playout, right? And you see, actually, if you go up to 30%, you pretty much cover a good portion. There's a couple cases you don't get, but there's these two cases you don't get, but we cover a very good portion. So 30% is kind of the number we assumed for our simulations. And so coming back to your question, right? So what we did is, if we look at a 50% prefix size, right, and N11, so cache and caching and so doing prefix, prefetching and caching in combination, then you see that if you have no scheme, right, you have a normalized load of 1. If you cache only, you reduce your traffic, right? If you prefetch only, you increase your traffic. But now if you do the combination of caching and prefetching, because of the reduction in the caching, right, you get a 1.2 normalized load, so there's a very slightly increase of the traffic, but you get a much better user experience. So with this approach, there's no reduction in load on the backbone network, but you really improve the user experience. So that was so we've realized that you see delay impulses quite often. We actually had another work where we did this. At this point in time, this was always with only a few users, a few locations. We actually then did you guys know Planet Lab? You heard of Planet Lab? Who doesn't know what Planet Lab is? Planet Lab is actually a test bed or an infrastructure has been set up for researchers across the world. So here are, for example, 2 Planet Lab nodes in the computer science building. But not only folks here on campus can use them, everyone who pitches in and makes some hardware available can use all the Planet Lab nodes in the world. And so you can run this for distributed experiments. What we did is we requested YouTube videos from nodes all over the world and saw how much pauses you have and all this. And we could, in a much more rigorous measurement, could show that the numbers we've seen here with the individual users really pretty much agree kind of wherever you are. Sometimes a little bit worse because it depends also on the access network and stuff like this. But pausing is a big issue. Prefix prefetching is feasible. The related videos are good interest predictors. They help really well. And prefetching can reach a hit ratio of up to 81%, while caching can only reach only a hit ratio of 40%. Okay? So we have a little bit more time, so I want to talk briefly to you. Oh, I want to stop and see if there's any additional questions. Sorry. I want to talk about one last topic, and that is actually where we got this idea of, well, if everyone is using the related list, can we actually use that even more to our favor? So what we looked at cache-centric video recommendation. And the idea is, if you have a video, or if you have a cache, right, and you request a video, you get the related list from YouTube, right? While this related list is pushed through the cache, you look if any of the videos in that list are already on the cache, and you push them up on top. Why is that? Because we have also measured that users very likely choose from like the top 10 of the related list. So with that little mechanism, you can actually kind of manipulate, if you want to say that strong, the user in choosing content that's already on your cache. So what we did here is actually, well, mentioned that before. We looked at, the requests, and again, this is data. This was from our prefetching paper. This is data from my colleague Li Xingao over in ECE for an IMC paper they had, and this is data from one of the current traces we had analyzed for this work. Is the requests that are made from the related list, right? So related list, 30, 40%, and as I mentioned before, there's another related work from colleagues that they've taken background traces where they even see up to 60%. So, the approach is what I think I just described the approach, and so, oops, this is Keynote. That graph, everyone tilt their head by 90 degrees, please, if you don't mind. So this is because my slides are originally PowerPoint, and we're using Keynote here, and split them up. So here we used 2 new traces, right? You have all the 2 3-day traces, one from February 2010 and 2012, and one from January 2010. You have the request numbers. Oh, actually, this trace we also used in the earlier work. This is the one from the winter break, right? Because the numbers are so low, then we got a newer trace from February 2 years later. And so what you see here is we use that trace information. What you see on the x-axis, which appears to you like the y-axis, but it's not, is the related video position in that list, right? So position 1, 2, 3, and so on. And the CDF of how often that position is requested in the trace. And you see if you go up, if this actually, does it work? No, unfortunately, these lines are drawn correctly, so forget about it. So if you go up to top 10 is it's somewhere between 70 and 80%, if I get this. Sorry, right? It's kind of hard to eyeball this when you tilt your head 90 degrees, but that's kind of we analyze that a little bit. So that shows you that there's a lot of requests coming from the related list, right? So so what we also did is when you do this kind of manipulation of the list, we want to make sure that we don't send people in a loop, right? And so what we did is actually we analyzed without modifying the list what kind of loops and chains you have already when you were just using the YouTube recommendation system. So, what we did is here, loop count is actually how many steps, or how many requests does it take you when you request videos from the related list until you come back to the video originally requested. And the chain count is actually how often do people use the related list until they use some other means to watch the list. And so we analyzed that. And so here, if you look at the chain count, right? So we have a chain count of 1 in trace 1, and 50 for 85%, and for 50% a chain count of least at 2, right? And then for trace 2, it's actually much higher. We have a chain count of least at 2 for almost 50%, right? While this is reduced to 84%. And so here you see the chain count, the average chain count, and then the maximum. Right? So people kind of use that to go watch videos by going through the list. Sorry. The loop count you see here, you see the position in the related video, and it should just say loop count here. How many videos it takes until you come back to the original video, and this is really surprising. So YouTube is kind of already keeping you kind of in that loop, right? This is just what we did is again we used Planet Lab to just hit that position over and over again by having a little robot that automatically did this request. And we figured out that if you always select from position 1, and we used it for different regions across the world, right? We did this for US, EU, Europe, Southeast Asia, and then South America. Thank you. And you see, if you always hit position 1, it only takes you 3 clicks on the related list until you come back to the video you originally requested, right? And so we said, well, let's take a look at this, and let's do this randomly, right? This was always clicking at the same position, right? And then we randomly took positions, and you see even there, if you do it randomly, you see you have a very high position of videos for sure. So up to like between 46% have a look count of 1. But then you have the rest of them all have look. So so we weren't afraid of introducing something new because YouTube is already doing that. Right? So they keep you kind of confined. It's very interesting. I don't know if you experienced that yourself when you've been watching videos and using the related list. So coming back, I'm really sorry about this. So coming back to, we talked about the cache hierarchy and the Google cache on campus, right? So when we did this, we said now, well, since they keep you in this loop, right? Can we check where like the top videos in the related list are served from, right? YouTube has a 3-layer cache hierarchy. So we have one cache on campus, there's regional cache, and then you go all the way up to like the origin servers, probably potentially in the West Coast. And so what we did is we used our analysis data, requested 100 videos from trace 1 and their related videos, and looked at the round trip time, right? And here you see the round trip time in milliseconds and the CDF. And as you can see, you have this is not turned around, but you can see you have 3 regions here, right? 1, 2, and 3. And then we looked at the traces we had because we did this is like analysis we did later on, right? We requested all of the 100 videos from a local box, right? And turned TCP dump on or Wireshark on to see where this is served from. And then we realized this is coming from an address in our network. Right? So this is our local cache. This is how we learned about the local cache. And then this is a YouTube IP address, and this is another set of YouTube IP addresses, right? And the interesting thing is then also, if you look at this graph, so we figured out there's a 3 cache hierarchy, right? And we can figure out where these videos are served from based on the round trip time. Now what you see here is actually, based on these round trip times, we could characterize which videos are served from what cache level, right? And there is no certain emphasis on serving more videos locally, right? So all this keeping you in the loop doesn't really agree with what would make sense of pointing to videos that are actually on the cache. So with that analysis, we could show that they're not doing already what we have in mind. Okay? So bear with me for a couple more minutes and then I'll be done. So unfortunately, this goes. So here's our approach, right? So we have the web server or the origin server here. We have the proxy caches. So if there's a request, you go through, you get the related list back. Here the proxy cache quickly checks, do I have one of these videos that come down a related list on my cache? Yes, video B is on here, so I push this up, right? In this case, actually B, C, and D are on there, so B, C, and D are pushed up, right? And so, again, let me just skip through this with respect to time. Where's this graph? So we took our traces, right? Trace 1 and trace 2 I showed you earlier, and just look at the position-centric approach. What we did here, the content-centric approach, is identical to the reordering where we said a user is really keen on the content. So if we reorder it, they follow the content. On the position-centric approach, we followed that users kind of are more, they just click on what's on top, right? And if you take this approach, you see that for this trace you go from 6.171% up to 11% hit rate, right? So you almost double it. And here it's increased by almost 5 times. Right? So you can really increase it. Now, there's one thing I want to mention to you. We have just done that lately. It's not shown in this data here. We have actually gone and had done a little user experiment where one of my students built a little Google Chrome plugin that when you install that plugin on your browser, we would manipulate the related list just randomly and have students, friends try that out and see what happens. And we still got the results that people, just choose very likely from top of the related list. So that's kind of a good indication that this is an approach that's working. Okay, a couple discussion things is like what's the cost? You add a little bit of extra work on the cache because you have to sort the list and these kinds of things, but it's not too high. And then also you can think of the reduction of the server load, right? Now with that, you reduce the traffic that has to be served from the server by quite a bit. Right? So it's not too much because these are smaller traces, but we believe that if you have that for larger groups, then this might increase. Again, popularity is based on the related list, and one of the things we want to look now in the future is actually how does this work with adaptive video streaming, where you have different versions of the same content in different quality, right? So I don't know if you guys heard about dynamic adaptive streaming over HTTP, where actually the quality can change over time based on what your available bandwidth is. But the way this is done now is with AVC encoding, so you have to have different versions of the same video in different quality formats on the server or on the cache. That's kind of a new problem that's introduced with that, and that's some of the stuff we're looking into. Okay, I think I talked about this all. See if you guys had any questions. Good. I'm over in the Notes Engineering building. If you ever have any questions later on, feel free to stop by us, shoot me an email. And thank you for coming. I hope you enjoyed a little bit what I was talking about, and have fun for the rest of the semester.